Hello students, in lecture 11 of your course Advanced Calculus, here we study certain aspects, some basic aspects through which we shall motivate the conceptualization of the maxima and minima of a function of two or more variables. So in order to define or to obtain the maxima and minima of a function of two or more variables through the concept of critical point, we have to define open sphere, closed sphere, and using open concept of open sphere, we can define the interior point and boundary point of a set, and after that the critical point, and then the procedure to find the maxima and minima of a function of two variables will be given, and certain examples are discussed over here in this lecture. So first we define what is the meaning of an open sphere. Suppose you have a point x0, y0 in R square. R square means the xy plane. Basically here this x-axis denotes a real line and this y-axis also denotes a real line. So this xy plane, basically we can also call it as a R square plane. And if we have a point x0, y0 in the plane R square, and R is any positive real number, that is R is any real number such that R greater than 0, then the set of all points of R, set of all points of R square that are included in the R neighborhood, of the point x0, y0. So geometrically you can visualize the situation. This is your plane, R square plane here, R cross R, and this is the point x0, y0 there in the plane, and let R is the positive real number. Now I'm drawing a circle here whose center is at the point x0, y0 and radius is R, and this purple line is denoting this blue line is denoting the boundary of this circle, and this purple line is denoting the radius of this circle. Now as we are saying in the definition, the set of all points of R square that are included in R neighborhood of x0, y0. That means around R neighborhood means if you draw a radius circle of radius R around this, and the points inside this dot dot, suppose these are given, then this shaded region denotes the open sphere. In the open sphere, the points of boundary are excluded. Boundary points are not. The points which are on the boundary of the circle are not included. So only then this shaded region will be called an open sphere, and mathematically it is represented in this way. This set is represented in this way: SR, R means the radius, and x0, y0 denotes the center of this circle. But you will say, or it is always a query in the mind, that here we are talking about a circle, but we are calling it as a sphere. In general, we call this as a sphere because if we move on to the R3 space, in the three-dimensional space, then the point will be x0, y0, z0, and the radius R, and then it will be a sphere. So depending on the dimensions of the space under consideration, the neighborhood changes its form. For example, in the 2 dimensions it is a circle. When we talk about the 3 dimensions, it will be a sphere. And if we further restrict the situation to R only, then on the real line R, the point will be simply x0, and if you draw the neighborhood R around it, means R on this side and R on this side. So in fact, in that situation, this neighborhood will be x minus R to x plus R. In fact, it will be the open interval. So in one dimension or on a real line, the open sphere means an open interval. In two dimensions, open sphere means a circle, the interior of a circle, in fact, interior of a circle, that is part inside this boundary is the open sphere. And if we move on to the three dimensions, then in that case the open sphere means the interior of a sphere. Interior of a sphere means excluding the boundary points, and the points which are on the boundary are called the boundary points. So if we further talk about the boundary point, that means here I have shaded the whole portion. Radius is r again, point the center is at x naught y naught. Then we have included the boundary points in this also. So boundary points are also there. Then this will be called a closed sphere, and it will be denoted mathematically. It will be denoted symbolically. It will be denoted like that: SR x naught y naught with square brackets, and in open sphere these are the round brackets. So this is the concept of open and closed sphere. Then the interior point and the boundary point. Suppose you have the domain D contained in R square. A point x naught y naught belongs to R square H, said to be an interior point of D if this open sphere is contained in D. Open sphere centered at x naught y naught, centered at x naught y naught is contained in D for some r greater than 0. That means you suppose you are having a point x naught y naught here. Suppose you are having a point x naught y naught here, then you will say that this point will be the interior point of set D. If around this point you can draw this blue line, this open sphere with radius r, and this is contained in D. This is contained in D. In fact, in that situation, I am considering D, this brown boundary. We are considering D. Then this is the open sphere. And in that case, if I am taking here, actually I have stuck it down. Then it is the x naught y naught is the interior point in this case. Now, if we talk about the boundary point, now I am striking out this point here, and I am keeping it here x naught y naught. And now I'm considering this part as D and the remaining part as r square minus D. In that situation, a point is here. That means this we are drawing a open sphere centered at this point, and this sphere consisting certain points from r square minus D part and certain points from the D, because in this situation we are assuming that this part is D. So this point will be called a boundary point. So you can see the definition here. X naught y naught belongs to R square is said to be a boundary point of D if and only if SRx naught means the open sphere contains a point of D as well as of R square minus D for every R greater than 0. Means why we are saying for every R should be positive, and it can be as small as possible and it can be as large as possible. So we can draw a very small open sphere, a very large, and like that. But for every R, there will be a point from R square minus D as well as a point from R square as well as a point from the set D. Then we'll say this, it will be a boundary point. So this is the concept of interior point and the boundary point. Now, what is a critical point? First, we talk about the critical point in case of a function of one variable. The critical point of a function of one variable is a point in the domain of the function at which either function is not differentiable, either the function is not differentiable, or value of derivative of the function at that point is 0. So same idea we can carry forward to the function of two variables. You are given a set D subset of R square, And f d to r, definitely it is a function of two variables. Why? Because d is in r square. A point x naught y naught belongs to R square is called a critical point of f if x naught y naught is an interior point of D, means this x naught y naught is an interior point of D such that either the divergence of, or you can say the gradient of f at point x naught y naught does not exist. Either the gradient of f at point x naught y naught does not exist, or the gradient of f at point x naught y naught exists and it is equal to 0, and it is equal to 0, 0. So mathematically, if we look at this situation, this gradient means, suppose I'm having this f of x y as a function of two variables, then what is the meaning of del f? You know, the meaning of del f is delta f means del f by del x comma del f over del y. So when we are saying that it is 0, 0, that means 0, 0, that means del f over del x equal to 0 and del f over del y equal to 0. So from this definition of the critical point, we can see the critical point of a function of two variables can be obtained if we put the first order partial derivative, both the first order partial derivatives equal to 0. By substituting these 0, we can get the critical point for a function of two variables. Now, the working rule to find the maxima and minima of a function of two variables. The first step is differentiate the function with respect to x and y, and we get these two first order partial derivative, and there are three second order partial derivative. Now to find the value of the point of maxima or minima, what do? We equate the first order partial derivative to 0 and solve these equations for x and y. After solving, we get certain values of x and y, and let AB be the value of xy. So this is basically a point of maxima or minima. Then how we identify that this AB is a point of maxima or point of minima? For that, we move forward to first we obtain the second order partial derivative del square f over del x square. We call it as r, and s equal to del square f over del x del y, and t is del square f over del y square. We obtain the value of r, s, and t at the point AB, and then check rt minus s square. If this rt minus s square is greater than 0 and r is less than 0, then we'll say that f of xy has a maximum value at the point AB. And if this is greater than 0 and r is also greater than 0, then you will say that f of xy has the minimum value at the point AB. Now if rt minus s square is less than 0, means negative, then fxy has no extremum value at the point AB, means it is neither a point of maxima nor a point of minima. Now further, if rt minus s square equal to 0, then the case is doubtful and needs further investigation. So we take the first example. Discuss the maximum and minimum of this function. Obviously, this is a function of two variables, so we can write f of xy equal to x square plus y square plus 6x plus 12. We find the first order partial derivatives, this one and this one. Then the second order partial derivatives, this, and this. Okay. Now first we find the point of maxima and minima. To find the point of maxima minima, or sometimes we call these as stationary points. Stationary points. What do? We equate the first order partial derivatives to 0. del f over del x equal to 0, del f over del y equal to 0. In fact, del f over del x is 2x plus 6. So you write 2x plus 6 equal to 0, then this is 2y, then 2y equal to 0. So here it gives you y equal to 0, and here it gives you x equal to minus 3. So we have obtained the point minus 3, 0. Now we want to investigate whether this point minus 3, 0 is a point of maxima or point of minima. So at minus 3, 0, the value of r is in fact this one. This is r, this is s, and this is this is s, and this is t. So you can see all these are constants. So whatever value of this point of maxima minima is there, we cannot substitute it here, so that we find the values of these second order derivatives at point minus 3, 0. So in fact these values remain same, means r will remain 2 and s remains 0 and t equal to 2. So rt minus s square means 2 multiplied to equal to 0 is 4, and this is of course greater than 0. And what is r? R is 2. 2 is greater than 0. So this is the situation. Now these two, when you look at the conditions, rt minus s square is greater than 0 and r is greater than 0. That means the function f of xy has minimum when x is minus 3 and y is 0. That means at point minus 3, 0, f of xy has a minimum, and the minimum value of the function at this point is obtained by substituting x equal to minus 3 and y equal to 0 in the function f of xy. So that gives you f of minus 3, 0 gives you 9 plus 0 minus 18 plus 12 equal to 3. So this is the minimum value of the function. Now let us see the example 2. Show that the function fxy x cube plus y cube minus 63 x plus y plus 12xy is maximum, means this function has a maxima at point minus 7 minus 7 and a minima at point minus 3 minus 3. So here f of xy is this thing, that is equation 1. We find the first order derivatives del f over del x and del f over del y. Then we find second order derivatives del square f over del x square, del square f del x del y equal to 12, del square f over del y square equal to 6y. Now for the points of maxima or minima, or for extremum, what do? We substitute the first order partial derivatives. We don't require this p and q. In fact, you simply say that first order derivative is this and we are equating it to 0. First order derivative with respect to y is this and equating it to 0. So after simplification, this gives you 2 and this is 3. Then we have r equal to del square f over del x square is 6x, and this is 12, and this t is 6y. Now by solving equation 2 and 3, we shall find the points of maxima and minima. So on subtracting 3 from 2, we get this equation. Further simplification gives you x minus y into x plus y plus 4. So from this equation, we can have either this part is 0 or this part is 0. When you consider that this part is 0, then you get x equal to y. And when you consider this part is 0, then x plus y equal to 4. So this is equation 4. Now we consider the first case. If x equal to y, then equation number 2 here, when you put x equal to y here, it becomes x square plus 4x minus 21. And from this equation, then you will have, after the factorization, x plus 7 into x minus 3 equal to 0. It gives you x equal to minus 7 and x equal to 3. Of course, x is equal to y. You are considering the case when x equal to y. So y becomes minus 7 and y becomes 3 in this situation. So the stationary points, we get two stationary points, minus 7, minus 7. means x is 7, y is 7. Other one is 3, 3. So 3, 3. On solving 2 and 4 further, we have this x plus y is 4. So that means you can say y equal to 4 minus x. And you substitute the value in equation number 2 again. Again, we get this equation. So in that situation, x is minus 1 and x is 5. And when you put this value, because you know, in that situation, y is equal to x minus 4. You are considering the second case when x plus y is 4. That means it gives you y equal to x minus 4. So when x is minus 1, from here y is 5. When x is, in fact, y is, sorry, here it will be 4 minus x. So when x is minus 1, so y is 5, and when x is 5 here, so y is minus 1. So we have further 2 points, minus 1, 5, this one, and this is 5 minus 1. These are 2 more stationary points. Hence, there are 4 possible extremum points. Means here are 4 possibility at which the function f of xy has maxima or minima. So let us examine all these and we construct a table for that. We know that r is this one, s is 12 and t is 6y, then rt minus s square is what? So we are having the points minus 7, 3, 3. I think some problem is there. I think it would be minus 7 must be there, and it should be 3, 3, 3, 3, and it should be minus 1, 5, and then 5, 1. So in this way, at this point, suppose you are putting here x is equal to minus 7. So value of r is minus 42. Value s is of course 12. And in t, when you put minus 7, it will be minus 42. And rt minus s square becomes 620. So now you can see for at this point minus 7, r is negative because it is minus 42. And rt minus square is positive. So that means f of xy is the point of is having a maximum at point minus 7. Similarly, at point 3, 3, you see the 3, 3 here. When you put x equal to 3 here, it gives you plus 18. When this will remain 12. And when you put y equal to 3 here, then again it is 18. And rt minus s square in this situation is 180. So again you can see here r is positive and rt minus s square is positive. So this is the case of minima at 3, 3. So that is what we wanted to prove. But here you can see for the other 2 cases, other 2 stationary points, this rt minus s square comes out to be negative. And in that situation, function has neither a point of maxima nor a point of minima for such kind of situation. So that is it about this lecture, and content has been taken. Some definitions from this book, Gorpare et al., A Course in Multivariable Calculus and Analysis. Thank you.